So hopefully you all recall, if we had a circuit that looked something like this, call this R, and this guy L. And our switch opened at t is equal to 0. Our inductor current as a function of time, IL of t, would always be of this form. IL at 0 minus for t less than 0 minus, and it would be IL at 0 plus e to the minus t over tau for t greater than or equal to 0 plus, where in this case tau is equal to L over R. And if we had a similar circuit, we know that VC of t would always be of the form VC at 0 minus for t less than 0 minus, and VC at 0 plus e to the minus t over tau for t greater than or equal to 0 plus, where for our RC circuit, tau was equal to R times C. That was our first order transient analysis, specifically source-free first order transient analysis for an RL circuit on top and an RC circuit on bottom. Today, we are going to look at what happens when we have an RLC circuit, and we are going to be using the form of how we know our RL and RC responses do to kind of guide our analysis. So today, specifically, we will talk about parallel RLC circuits. All right. So let's say that I have something similar to the previous two circuits that I've drawn, a practical current source. Switch that opens at t is equal to 0. And then I have a network that contains a resistor, and inductor L, and a capacitor C, all connected in parallel like so. So when the switch is closed at t is less than 0, there should be some amount of energy stored in the inductor. I'm saying that because at t less than 0, when the switch is closed, we have our current source in parallel with 2 resistors, an inductor, and a capacitor, and we're at DC steady state. So all of that current IS should be flowing through the inductor, which means that inductor has some stored energy. As soon as that switch opens up, only the RLC network remains. Effectively, the source will have no effect on the RLC network, and all of the energy that's stored by the inductor, some of it will be transferred to the capacitor to charge it up, and some of it will be dissipated as heat in the resistor. And so what we're going to try to figure out today is how that looks mathematically. So I am going to define a few figures of merit here. The first of which will be the voltage V of t. Now this is the capacitor voltage, which means we know that it cannot change abruptly with time, but it also represents the inductor voltage and the resistor voltage, because the resistor, capacitor, and inductor, R, L, and C, are all directly connected in parallel. So this one voltage is characteristic of all 3 things, but we need to keep in mind specifically, it's a capacitor voltage, it cannot change abruptly, all right? Another few figures of merit that we might have to pay attention to, and we definitely will have to pay attention to actually, is our resistor current, IR of t, our inductor current, which I'll draw down here because I'm running out of room, IL of t, and our capacitor current, IC of t. So during the transient condition, after our switch has opened and disconnected our practical current source, if we applied Kirchhoff's current law to our topmost node, we would get the relationship IR plus IL plus IC is equal to 0, right? All 3 currents are leaving the top node, so they're all, when we add them together, set it equal to 0. Just straightforward application of Kirchhoff's current law. Now, we can relate all 3 of those quantities to that common voltage that occurs over all of those elements. So the voltage drop over, or excuse me, the resistor current expressed in terms of the voltage drop is just by Ohm's law. So if V is equal to I times R, then I is simply V over R. So we're going to have 1 divided by R multiplied by V of t. The current through an inductor as a function of voltage is the integral, 1 over L multiplied by the integral from t naught to some later point in time of t, multiplied by the voltage as a function, I'm going to say of x, where x is a dummy variable for time, plus whatever initial condition we have on the inductor current. I just flung my stylus over here. And lastly, our capacitor current is given by C dV by dt. We set it all equal to 0. Or we could move the initial condition on the capacitor, the inductor current to the other side. So what we have here is an integro differential equation, okay? And integro differential equations are annoying. So what I'm going to do, and there's a perfectly valid mathematical move here, is I'm going to take my integro differential equation and convert it into a second order differential equation by just taking the derivative of both sides, okay? So if I take the derivative of both sides with respect to time, I get rid of my integral, which is the thing that really complicates this guy. So that would leave me with, and I'm going to move things around a little bit. Let's see, C times the second derivative of the voltage with respect to time plus 1 over R times the first derivative of the voltage with respect to time plus 1 over L times the voltage function itself. When I take the derivative of the integral, I get the function. And this is equal to 0. Taking the derivative of the initial condition, this is a constant value, so that goes away. One last thing that I am going to do is I'm going to divide everything by C so that the coefficient on my second derivative term is 1. So finally, I will have the second derivative of V of t divided by dt squared plus 1 over RC times the first derivative of dV by dt plus 1 over LC times VT is equal to 0. So this is the characteristic equation for my parallel RLC circuit. All right. So we need to formulate a guess as to what the voltage waveform in this circuit is going to behave. And I would argue that based on our prior experience with our RC circuit up here, we should guess that it's going to be some exponential form. Okay. So I'm going to guess that V of t is going to be of the form A, some initial value, E to the ST. Based on my experience with these types of circuits, when I plug this guess value in, so the second derivative of A, E to the ST is going to be S squared AE to the ST. Is that correct? Let's make sure I'm doing my calculus right. So the first derivative is going to be S AE to the ST. The second derivative should be S squared AE to the ST, I believe. Plus 1 over RC S AE to the ST plus 1 over LC AE to the ST is equal to 0. And I can algebraically rearrange this a little bit. Like so. So I pulled the common factor of A out, and I pulled the common factor of E to the ST out. And so what I'm left with is A multiplied by the quantity S squared plus 1 over RC multiplied by S plus 1 over LC multiplied by E to the ST is equal to 0. So our ultimate goal is to figure out how this thing is going to go to 0. If A is 0, everything is 0. And so this is the trivial solution and actually provides us no feedback whatsoever on how this guy is going to behave. E to the ST could approach 0 for specific values of S. So if S were negative and large, as time progressed, it would eventually settle to really close to 0, but it's definitely not 0 at all points in time. So what we are going to try to figure out then is what value of S will make this middle bit settle to 0. If you'll notice, that is a simple second order quadratic equation. So we can use the quadratic equation to find it. So in this case, A is equal to 1, B is equal to 1 over RC, and C is equal to 1 over LC, right? So using the quadratic equation, S1 and 2 will be equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. That's good old 8th grade math. And so when we plug in what we have, what we are going to get is, let's see, S1 and 2, negative B, so that's negative 1 over RC plus or minus the square root of 1 over RC squared minus 4 1 over LC all divided by 2, or negative 1 over twice RC plus or minus the square root of 1 over twice RC squared minus 1 over LC square root squared. And I know this is going to seem, let me redraw this a little bit better. Writing it in this way seems a little bit weird, but we are going to identify these parameters, okay? So I am going to define alpha as 1 over twice RC. Alpha is what's known as the Neper frequency. It has units of Nepers per second, which is effectively the same thing as 1 hertz, or 1 per second. What the Neper frequency is it gives us an indication of how this signal is going to decay. So it is very similar to the role the time constant plays in first order circuits. I'm going to define omega naught as the square root of 1 over LC. All right. This is what's known as the resonant frequency. It has units of radians per second, which is effectively the same thing as per seconds. Okay. Resonant frequency is something you guys are going to talk about a whole heck of a lot when you get into resonant circuit analysis in circuits 3. There's multiple different ways to interpret it. So one particular thing about the resonant frequency is if we found the resonant frequency of a circuit in a sinusoidal steady state system, the resonant frequency is where the impedance of the network is purely real. So at resonance, the capacitive reactance cancels out the inductive reactance. Another way to think about the resonant frequency is, specifically in filters, this is the frequency at which you get maximum amplitude. So how many of you have heard of the Tacoma Narrows Bridge? So that is a bridge that was built, I think, in the 1940s. And it's the one that collapsed when the wind caused oscillations at the resonant frequency of the bridge, causing the amplitude of the vibrations in the bridge to amplify over and over and over again until it literally ripped itself apart. If you've ever seen, yeah, there is absolutely videos of that. If you've ever seen a construction site that uses scaffolding, if you set up your scaffolding and you tap it with a wrench, what you hear, the audible tone, that is the resonant frequency of that system. And that's actually one way they test to make sure that the scaffolding isn't going to fail. So if you load up the scaffolding and you hit it and you hear high frequency, you're great. As you put more and more weight on it, it's going to cause the frequency, the resonant frequency to decrease until when you get to a low frequency. So if it sounds like a ping, you're good. If it sounds like a thud, it's about to fail. That's how lay construction people can tell whether or not they've loaded up their scaffolding and stuff like that with too much weight as a safety measure, just as a real quick check on things without having to do lots of load calculations and this, that, and the other. So resonant frequency has lots and lots of interpretations. Here in this particular class, it's going to be related to the oscillation frequency that we'll see whenever we form effectively an LC tank, but we'll talk about that in a little bit. So with those definitions in mind, we can say that S1 and 2, the eigenvalues of our system, come to negative alpha. Actually, let me not do 1 and 2. S1 will be defined as negative alpha plus the square root of alpha squared minus omega naught squared. And S2 will be negative alpha minus the square root of alpha squared minus omega naught squared. All right. So now that we know the eigenvalues of the system, our generic solution, V of t, will be of this form. A1 e to the S1t, so that's one solution, and A2, so a different initial condition, e to the S2t, is also a solution. And because of the superposition principle, if I have multiple particular solutions, the general solution is simply the sum of all of the particular solutions. Now, I also want to point out, excuse me, one other thing here. There are 3 different conditions that we can have with respect to alpha and omega naught. So when alpha is greater than omega naught, we consider our system to be over damped. In an overdamped system, S1 and S2 are negative and real, meaning they have a discrete value that is not imaginary, okay? And our response, generically speaking, y of t, will be of the form that we've previously discussed. A1 e to the S1t plus A2 e to the S2t. When alpha is exactly equal to omega naught, which can happen, we consider our system to be critically damped. In a critically damped system, S1 is exactly equal to S2. Now that creates a little bit of a problem here, because if S1 and S2 are equal to each other, we could simply add A1, so we would have A1 e to the ST plus A2 e to the ST would just be some new coefficient multiplied by e to the ST. The problem with that is that there's no way we can satisfy two different initial conditions, right? So we're going to have some initial condition on the capacitor voltage that needs to be satisfied, but we also need to have an initial condition on the inductor current that needs to be satisfied. So we have to slightly change our response. So in this particular case, y of t will be equal to A1 multiplied by t e to the minus alpha t plus A2 e to the minus alpha t. The reason why they are raised to the minus alpha is if alpha and omega naught are equal, this guy goes away, right? So S1 is exactly equal to negative alpha and S2 is exactly equal to negative alpha. And so we have to adjust our response slightly to give us a way to solve for these two different initial conditions. I am not deriving where that comes from. A, because I don't know how to off the top of my head, and B, because you'll go into that probably on literally the first day of Math 245 as well as ELEN 321. So you'll learn the derivation of where that comes from elsewhere. Our third case occurs when alpha is less than omega naught. And this system we consider underdamped. So let's look, let me scroll back here a little bit. If alpha is less than omega naught, what happens to the bit under our radical here in our definition for S1 and S2? Yeah, so we have the square root of a negative number, which means we're going to have some real part plus some imaginary part. So it's going to be complex. And it's going to turn out that S1 and S2 by definition will be complex conjugates of each other, always. So S1 is the complex conjugate of S2. And in this case, we're also going to alter our response equation, but it's purely to make the math less annoying. So if we apply Euler's identity, which says that e to the alpha t is equal to sine alpha t plus j sine alpha t, we wind up getting the following expression. B1 cosine omega dt plus B2 sine omega dt e to the minus alpha t. Excuse me. So the cosine and sine part come about from applying Euler's identity. Omega d is defined to be omega naught squared minus alpha squared. So it's simply the same thing as the radical part of S1 and S2, but we change the sign on it. And this is known as the natural frequency of the system, measured in radians per second. So I have created a table that is available to all of you on the course's Moodle page, and I'm going to go ahead and pass around these physical copies to those of you that are here. And what I have done is, in this table, you can use it for both parallel and series RLC circuits. Tells you how to calculate alpha, how to calculate omega, tells you if alpha is greater than omega, you have an overdamped system. Alpha is equal to omega, you have a critically damped system. Alpha is less than omega, you have an underdamped system. Gives you the general response equation for y of t, and I also give you the derivative of y of t. And that's going to be critically important, as we'll see when we actually solve a circuit. So let's put this to use. I'm going to make up a simple circuit here. And walk you through the steps to determine our quantities of interest. So let's define them real quick, just to be clear. V of t, and let me make it less just explicit, so it's just V of t. Here's IC of t. Here's again IL of t. And here is IR of t. So one thing that I want to point out here, excuse me, is that we are never going to be able to solve for the quantity IR of t directly. And we can really only solve for the quantity, the voltage drop over the resistor, by solving for the voltage drop over the capacitor first. They're going to be the exact same thing. But the problem that we're going to face, why we're never going to deal with resistor quantities first, is because in the capacitor and the inductor, there is a derivative-based relationship between, so for the capacitor, if the voltage is a quantity of interest, the current gives us a relationship that involves the voltage that also involves the derivative. So we have two equations involving voltage and current in a capacitor, and we have two initial conditions that we can take care of. Same for the inductor. But for the resistors, since they can't store energy, we don't really have an initial condition that's stable to be able to deal with. So let's take this circuit and let's explicitly try to find our capacitor voltage and our inductor current and our resistor current. This will probably take us the rest of the class period. Once we're finished with this, we should be good to go, okay? So the first thing that we need to do is to determine alpha and omega naught and see if this circuit is overdamped, critically damped, or underdamped. So step one, calculate alpha and omega naught. Alpha, we know for a parallel RLC circuit, is 1 divided by 2 RC. So that's going to be 2 times 8 times 0.5. farads here is going to be 1/8 or 0.125 nappers per second. If I did that math in my head, I think 1/8 is 0.125, so that's fairly straightforward. Omega naught is going to be 1/LC to the 1/2 power, which is the same as, let's see, what's L? 1 Henry times 1/2 of a farad to the minus 1/2 power. So the square root of 1/2, calculator. Oh goodness, where's the square root sign on these Casios? There we go. Square root of 1/1/2 is the square root of 2, which is, no, good God, no. 1.414 and change. So we can see that omega naught is larger than alpha. So do we have a critically damped circuit, an overdamped circuit, or an underdamped circuit? Underdamped, right? So alpha is less than omega naught means that we have an underdamped system. And while we're at it, we may as well go ahead and solve for omega d, which is again going to be the square root of omega naught squared minus alpha squared. So that is 2 minus 0.125 quantity squared. The square root of 127/64. 1.409 radians per second. You know what? I lied. We're not going to calculate IL because I want to take that time to show you how to verify things on LT Spice. That will be a better use of time. All right, so we've calculated alpha and omega naught. Now what we need to do is determine our initial conditions. So we have to analyze the circuit at t is equal to 0 minus and analyze the circuit at t is equal to 0 plus. It's critical that we do both t is equal to 0 minus and t is equal to 0 plus here. So t is equal to 0 minus, let's see, we have 4 amps, resistor, resistor, there's our inductor, what are the values of these bad boys? 8 ohms, no, 8 ohms goes here, 2 ohms, all right, so we need to find out these quantities. D at 0 minus is going to be what? Zero. Why? Right, so the voltage drop over the short circuit that is representing the inductor, by definition, must be 0 volts. What's IR at 0 minus? 0 amps, because all of the current is going to flow through the inductor. IL is obviously 4 amps, and IC is obviously 0 amps. So we have analyzed the circuit at t is equal to 0 minus. They won't all be this easy, but it's going to be pretty darn close. So there's only so much variation I can throw on these guys. Now we analyze the circuit at t is equal to 0 plus. So let's see. Our inductor is going to be at the specific instant in time, t is equal to 0 plus. Our inductor is going to behave like a current source having the same direction as IL at t is equal to 0 minus and the same magnitude. So we have a 4 amp current source like so. Our capacitor is going to act like a voltage source, which has the exact same voltage polarity and magnitude as V at 0 minus. So if it was a 0 volts, or if it's acting like a 0 volt source, that means it's a short circuit now at this specific instant in time. So here is V at 0 plus. Here's IC at 0 plus, IL at 0 plus, IR at 0 plus. So V at 0 plus has to be 0 volts because the voltage drop over the capacitor cannot change abruptly. IL at 0 plus must continue to be 4 amps because the current through an inductor cannot change abruptly. Let's see, IR at 0 plus is going to be what? 0, because there's still that short circuit over there on the right-hand side. So none of the current will branch off and flow through the inductor, or excuse me, the resistor. IC at 0 plus is going to be what? Negative 4 amps, because IC is defined as the current flowing from top to bottom. So this 4 amps is going to flow from bottom to top, so it's negative 4 amps. All right. Now we are ready for step 4, which is effectively the final step. We apply our response equation. All right. So we know that because this is a underdamped system, V of t will be of the form B1 cosine omega dt plus B2 sine omega dt, sorry, I'm forgetting the t, e to the minus alpha t volts. At exactly t is equal to 0, what does this reduce to? So at t is equal to 0, what is cosine omega dt? 1. So we're going to have B1 times 1 plus B2, what sine omega dt at t is equal to 0? 0. So we have B1 times 1 plus B2 times 0, all of that multiplied by e to the minus 0. So what's e to the 0? 1. So that means that at t is equal to 0, V naught is simply equal to our coefficient B1, which we know to be 0 volts. Now, This is where the derivative-based relationship comes in. Our capacitor current, IC of t, is, by definition, C dV by dt. Instead of having to take the derivative of this thing every damn time, which would be wildly tedious, that's why I made the table that has the derivatives of the response equations on it. So just using our table explicitly, this becomes C times the derivative where it says the underdamped bit. So that's going to be omega d b2 minus alpha b1 cosine omega dt minus omega d b1 plus alpha b2 sine omega dt e to the minus alpha t. So I'm not going to make you guys do that derivative over and over and over again. That's what the table is for. At t is equal to 0 plus, what does this guy reduce to? So this guy goes to 1, this guy is 0, this guy goes to 1. So I would argue that IC at 0 plus is just going to be C times omega d b2 minus alpha b1. And this is going to have a value of -4 amps. All right, so scroll down here a little bit. We have -4 amps is equal to C, which is 0.5 farads, where a farad is an amp second per volt. I think. Let me double check that. Let me look. Yes, amp second per volt. Multiplied by omega d, which we know to be 1.40 something. Let me go up here real quick where we drew it. 1.409. Radians per second times B2, which we don't know, minus alpha, which we do know, but it's being multiplied by B1, which is 0. So I'm going to leave that part off. So we can solve this guy. B2 is going to be -4 amps divided by 0.5 amp seconds per volt times 1.409 per second. So this amps cancels that amps, this second multiplied by per second. So we have 1 over volts, which is going to give us units of volts. This is an important thing here. We're noticing, excuse me, B2, if we look up here, is the coefficient of the capacitor voltage. So if we didn't get units of volts here, we're screwed, all right? So I'm just making it explicitly sure you guys understand where the units of this thing are going to lead us. So better calculated, but I don't know what I did with it. All right. So we have -4 over 0.5 times 1.409. Gives us -5.678 volts. If I did my math correctly, you guys got calculators and can verify that, but that seems reasonable. -4 divided by roughly 0.7 should be a negative number that's a little bit larger than 4. So seems legit there. So from this, our capacitor voltage V of t is -5.678 sine 1.409 t e to the minus, what was alpha? 0.125. Volts. All right, because B1 was 0, so that means we shouldn't get a cosine term. All right, so I want to be very, very clear about the steps that I did here because you are going to be repeating them ad nauseum. All right. Step 1, calculated alpha and omega naught and determined whether the system was overdamped, critically damped, or underdamped. Step 2, we analyze the circuit at t is equal to 0 minus. Step 3, we analyze the circuit at t is equal to 0 plus. Step 4, we applied our response equations where we use our response equations and then set t is equal to 0 plus and able to set up a system of equations that would allow us to calculate B1 using the voltage equation and B2 using the current equation. It is very, very important that your first equation comes from the normal function and your second equation comes from the derivative. So if, for instance, we had tried to determine the inductor current would have been our first equation and the inductor voltage would have been the second equation that we used because the inductor voltage has the derivative-based relationship. You can do it the other way around using the integral relationship, but the math is way more complicated. Avoid it like the plague, okay? We plugged in our values from our initial condition bits, and we're able to solve for our two coefficients. And then we simply plug those coefficients directly into our response equation. If we wanted to find the inductor current right now, it would be trivial. Because C, omega D, B2, alpha, and B1 is, we could literally just plug all those things in here and we would get our coefficients for our inductor current as well. We wanted, I believe, to also solve for our resistor current. How are we going to get the resistor current based on what we have? So we know V of t. How do we get the resistor current? Use Ohm's law, divide it by 8, and we're good to go. Bless you. Negative 709.723 sine 1.409 t e to the minus 0.125 t milliamps. All right. Any questions about this before we hop into LT Spice and verify our solution? Nobody got anything? You need a minute to copy this down? All right. All right, so let's move this guy out of the way. I need a resistor, an inductor, and a capacitor. They're all in parallel. Let me wire them up. All right, so let's see, our resistor value was 8 ohms. Our inductor value was 1 Henry, right? I'm going to make sure here, it won't matter on this particular problem, but get in the habit of always setting the series resistance of your inductors to 0 ohms, because if you have very small resistor values, it sets it to 1 milliohm if you don't do anything, but that 1 milliohm can actually screw some of the. So get in the habit of setting it to 0. Our capacitor was 1/2 of a farad, I believe. All right, so we're going to set some SPICE commands. This is where we're going to put in our initial conditions. So we are going to analyze only for greater than t is equal to 0 plus. So the initial condition on our capacitor voltage was 0 volts, right? The initial condition on our inductor current was 4 amps, right? So I'm going to click OK, throw that down here. Let's see. Alpha is 0.125. Let's look at this thing over per second. So simulate. I'm going to do a transient analysis, and I think 1 second should be long enough, but if not, I'll change it in a minute. Let's run this simulation. So our capacitor voltage is this guy. It settles. Let me do it for longer. Still not long enough to settle. This is probably far too long, but we'll go with this. Yeah, all right, so looks like it's totally settled down at about 50, but this is good enough. Well, no, I don't want to get you guys in the habit of being lazy. Let's change that to 50. So what I want to see before I run this, so what I'm expecting to see when you guys submit your graphs and stuff like that, is that it settles to its final value with only minimal oscillations. So if you gave me a graph of what's happening between 0 and 10 seconds, it's very obvious that it has not yet settled. Even at 20 seconds, it's pretty obvious that it hasn't settled. 30 seconds, there's still a significant amount of ripple in this. At 50 seconds, we're probably talking about on the order of a couple of millivolts of ripple. That's probably good enough for me. Out at 60 seconds, we can see that it's pretty well flatlined, okay? That's how much I want to see. I don't want to see something, let me change this real quick. I don't want to see something like this where all of the information is on one side of the graph and you can't really tell what the hell's going on. So I want your time duration for your transient analysis to be effectively just long enough to get a full picture of what's going on, not any longer than that. And you're just going to have to play around with things here. So like my basis, and I did the math in my head improperly, alpha in this case was 0.125 seconds. So if I treated alpha as the effective time constant for this thing, that would mean that my time constant would be 8 seconds, because alpha is 0.125 per seconds. Flip that over is 8 seconds. So 5 or 6 time constants should get me down to, settling to really, really close to its final value. So that would have been somewhere between 40 to 50 seconds. So that's, if I had done the math correct the first time, I wouldn't have had to iterate through it, but I got to show you some stuff I wanted to talk about anyway. All right, so here's our capacitor voltage. Now, let's talk about how we go about checking our answers. So I'm going to add a trace, and I'm literally just going to put in the mathematical function that we got through our analytical solution here, which was negative, read it off to me. 5.678, was that what you said?
Yeah.
All right. Times the sine of 1.409. All right, so here's an important thing here. All right. LT Spice takes everything in terms of degrees, even this. 1.409 is the angular frequency expressed in radians per second. So we need to force it to be interpreted as degrees per second. So I'm going to multiply this by 180 over pi. If I don't do that, it's going to screw everything up. Then to multiply by t, LT Spice doesn't, the variable is literally the word time. So time multiplied by exp negative 0.125 times time. And I believe I put all that in correctly. Syntax error is what? I need one more parentheses. I don't have to put volts here. I could. We'll talk about that in a second, but I had the parentheses for my conversion factor. I had the parentheses for my sinusoidal function, but I did not have my parentheses for the bit that's being multiplied by the exponent. That's my best guess is what is going on here. Boom. My curve for our mathematical expression and the simulation matched exactly. This is how I know I did it right. Okay. So there is literally no reason you should ever get any of these problems wrong in your homework. It will match perfectly. If it does not match perfectly, either you have made a mistake setting up your simulation or you have made a mistake in your math. Yes, sir.
Can you change the L1 resistance to the default just to see what effect it would be?
So in this one, it would be trivial because R1 is 8,000 times larger. So if I take this off and I rerun my simulation, it's nothing. Yeah. But if R1 was on the order of, say, 0.1 ohms, so still 100 mega ohm or 100 milliohms, that would still be enough to wiggle it. I think I have all of your homework problems set up to where it shouldn't matter, but the first couple of times I taught this class, or like the first year I taught this class when I did these, I had one problem where I made the students solve for the R value that would make it critically damped or something like that. And it turned out to be on the order of a few milliohms. And if you don't turn that off on your inductor, your simulations never matched, even though you were exactly right. So just get in the habit of doing that, just for argument's sake, but it should not, I believe I have the problem set up now to where that should not bite you in the butt. All right, any questions about the simulations, the math or anything involved or any of that jazz? Will LT Spice give it to you? No.
Even if we already have, it already has the.
Yeah, no, it already has it. I have no idea. Not that I know of. You're free to look for it. I've always just done the simulation and did the math and then plotted them both on the same plot and made sure it was the same. In fact, that would be my preference. I mean, I guess you could bullshit your way through all the work and then be like, look, here it is. But to me, it's easier to just do the math and then check it this way. Or you can, you know, reverse engineer LT Spice if you want to. We'll see. All right, if there aren't any other questions, then when we get back from the break, we will handle series RLC circuits. And then the total response, which is really, really easy. It's already on the thing I gave you. You literally just add y at infinity to all of your y of t equations, but don't add it to the derivative. And then we get into general RLC circuits, which are more math intensive at the front end. And then once we figure out what the characteristic differential equation is, it's literally the exact same thing. So get used to doing these couple of steps that we did over and over and over again for the next 2 weeks. What it is. All right, you guys have a great rest of your break. All that jazz.
One of these are on the homework, right?
Pardon?
One of these has probably homework that's due being at the end of the day.
No. So this is going to be an entirely new homework set. So this will be due. This homework set will be due the Friday after you get back from break. Yeah, there shouldn't be any RL circuit type stuff on anything you have to do immediately during the break. All righty, catch you guys later.
See you next year.
Yep, see you next year.